You are muted. You are muted. Sorry.
Yes, it goes better without the mute. So thank you, and sorry about this. So first, I'd like to thank the organizers for inviting me to speak at this conference. It was a very good morning so far. I want to talk about the tidal deformation of black holes. And in particular, I want to talk about this business that tidal love numbers for black holes vanish. There's been a lot said about this over the last, I don't know, 15 years, something like this. And I would like to give you a personal view of this topic. I insist it's a personal view. It may not be shared by all, but that's the view that I think is the most useful and the most constructive way of thinking about these things. And I'll just highlight that it's based on two papers that I published earlier in the year, and this one here is brand new. Okay, so I'm still having that trouble of not being able to scroll. Apologize, I'll have to. Okay, I really don't know what to do about this.
But what's the issue? Because it seemed to work fine the last time we were.
I switched something off, and that seems to have triggered it. So sorry. I think I'm fine now. Let me go back to sharing. Right, okay, now it works. Okay, so here's what I want to do here. I want to describe the tidal deformation of some body. And so it's going to be a black hole later on in the talk, but for the time being, it's going to be either a neutron star or a black hole, or in fact, it could be any sort of body whatsoever. And I want to do this in a context where the object creating the tidal field, that companion body here, M prime, is situated at a fairly large distance compared to the scale of the body itself. So I will claim this separation of scales because mostly I want the tidal field to be changing slowly with time, which will be the case if the orbital motion is slow, and that will be the case if the orbital separation is fairly large. So that's the first statement that I want to make, is that I'll be working in this regime of static tides where we are assuming that the time scale associated with changes in the tidal field are long compared with the body's own internal time scale. So that's the first thing. The other thing that I want to say is that I want to describe the tidal deformation of the body, or at least the tidal deformation of its gravitational field, in a neighborhood of the body, and I'll call that the body zone. And that's going to be where most of the action in this talk is taking place. And I really insist that what we're doing here is to isolate a neighborhood of the body, and we want to describe the tidal deformation of the body's gravitational field in that neighborhood. So that's what I'm calling the body zone. And for me, this is a region of space that's limited by that distance, R max. That's the boundary of that red region over here. And that boundary is going to be small compared to the interbody separation, B. So those ideas of slow evolution and also restriction to a limited neighborhood around the body, those are essential ideas for what I'm trying to do here. All right, so let's start in Newtonian physics, where we can talk easily about things, and I'll do that first, and then I'll look into promoting all of this to general relativity. So the idea of introducing that body zone and introducing a region of space where R is going to be small compared with B, the interbody separation, is that I can use the smallness of this ratio here as a way of doing a Taylor expansion of the external potential in powers of that small quantity. And effectively what happens there is that we're creating a multipole expansion for the external field, but instead of being a decaying multipole expansion as we normally expect, because I'm expanding in this ratio, what I'm finding is that, well, this is actually a growing multipole expansion in the sense that at leading order, I get something that grows as r squared in the description of my external tidal field. And if I were to carry more terms in that expansion, they would behave as r cubed, r to the fourth, and so on. So the purpose of working in a body zone is that I can really introduce this multipole expansion in growing powers of r to describe what is causing the tidal deformation of my body. The curly E is the coefficient in front that will scale like the external mass, and it will scale inversely with the interbody separation cubed. That's something I can call the tidal quadrupole moment. It basically gives me a characterization of the strength of the tidal field acting on my body. And that's supplied, of course, by the external companion, the thing that's responsible for creating the tidal field in the first place. So once we do this, then the task is to determine the potential of my deformed body within the body zone as amended by the fact that now we have a tidal field applying to the body. And if I do that calculation, and here I'm looking at the potential of my deformed body outside of it, so it's the exterior potential, what I find for the Newtonian potential of that body is the usual m over r term that it would get in the absence of a tidal deformation. And then I get two types of tidal corrections. The first is, well, the one that I introduced by introducing that companion, so that's the growing term. And then I have an extra term that corresponds to the fact that as I introduce the tidal forces, I'm causing a rearrangement of the mass inside the body. So there's going to be a tidal deformation, creating a tidal bulge. And that will create a deformation of the body, and that creates a deformation of the gravitational potential outside the body. And that has the form of a decaying term in my multipole expansion. So now we have both a growing term and a decaying term, the growing term being the description of the external tidal field, the decaying term being the response of the body according to that, in response to that applied tidal field. That number in front is something that will encapsulate the details of this rearrangement of mass inside the body. It's called a love number, and we have a love number for each multipole order of this expansion. And here I'm just truncating everything at leading quadrupole order. So different bodies with different internal structures will deform differently, and all of those details will be incorporated in that one number over here. Everything else turns out to be universal. So the fifth power of the radius, and of course the decaying power of r. Now, what we're dealing with here when we're looking at the external potential, we're really dealing with a solution to Laplace's equation. And we have both growing solutions and decaying solutions. And the decaying solutions to Laplace's equation are basically terms you would expect in a multipole expansion in inverse powers of r. So in Newtonian theory, there's a one-to-one, very immediate relationship between the love numbers that we introduce here and the mass multipole moments of my deformed body. And at quadrupole order, that means that the tidally induced quadrupole moment of my body can be related to the applied tidal field. It can be related to those powers of the body's radius, and it can be related directly like this to the love number. So we have this very clean, very immediate relationship between love numbers and tidally induced multipole moments. So that's an idea that we have in Newtonian theory. What I want to do now is to promote this to GR, general relativity. And what I'll be saying in the next few minutes is that it's straightforward to promote this relation here for the external potential. It's straightforward to promote that to GR. It's far less straightforward to promote this to GR. And I'll explain the reasons, and I'll explain what I mean by all of that. All right, so now we move to the relativistic theory. And as I said, it's going to be straightforward to promote the Newtonian potential to the full metric of a tidally deformed body. But before I do this and explain what's in that slide here, I want to really go back to this notion that I'm still working in that body zone, that neighborhood around the body that is small compared to the interbody separation. And when I write down that metric over here, it's really a metric that's valid here, and it doesn't extend beyond the body zone. It doesn't extend beyond this neighborhood. And that turns out to be an important idea. And it's something that I insist on because it's important to appreciate that fact that the metric that I'm constructing is limited to this region of space-time. So what do I get when I do this in GR? Well, I won't write down the expression for the full metric. I'll just write down the time-time component, and I'm working in a certain gauge and perturbation theory and all of this. But what I'm saying here is that we see exactly the same features in the metric as we saw in the Newtonian potential. So we have first a background term that corresponds to the unperturbed Schwarzschild solution. So F here is the usual Schwarzschild factor, 1 minus 2m over r. We have our growing term describing the tidal field, and we have our decaying term describing the response of the body to that tidal field. The only thing that's changed now is that instead of having a clean factor of r squared here and a clean factor of 1 over r cubed here, I have things that represent relativistic corrections to that. In the case of the growing tidal field, the relativistic correction is in fact just 1. But in the response, we have this rather complicated expression here for B, which if you write it down as a relativistic expansion, it starts at 1, and then we have correction terms of order m over r, and then it keeps going forever. One thing to notice here, and that's going to be important in just a second, is the fact that this quantity B here has a logarithmic divergence when f goes to 0. If m here is a normal material body without an event horizon, that divergence is of no concern. But if the body is a black hole, that divergence will be of concern. And that's the distinction between a material body, such as a neutron star, and a black hole. All right, so here's point number 1. Point number 1 is, as I said, it's straightforward to generalize the expression I had before for the Newtonian potential to GR. And we get this. In this description, that again is limited to the body zone, the love number K2 is a property of the deformed metric. It's a number that appears in the deformed metric that tells us something about how different bodies of different internal constitution will deform. But it's fundamentally, in my view, a property of the deformed metric defined in this local neighborhood of the body. And I claim it's nothing more than that. Conceptually, it's nothing more than that. And part of the reason why there's been a lot of discussion about love numbers in the recent past, and why some of that discussion tended to be, heated and passionate, is the fact that I think the love number tends to be overinterpreted. And I really want you to, take my word here, or take my point of view on this, that the love number is first and foremost a property of the deformed metric defined in this neighborhood, and nothing more than that. All right, so that was the first thing, the generalization of this. What about the generalization of that to GR? That's where it gets complicated. And the reason why it gets complicated is because, before I get to that, I just wanted to make a side remark that Sam Gralla made a few years ago about the fact that there's nothing sacred about the definition of love numbers. So my introduction of love numbers here was based on this distinction between the basis function r squared a and the basis function r to the minus 3 times b. Those are the basis functions that I'm using to decompose my perturbation into a tidal field and a body response. What Sam pointed out is that, well, you can always add a small decaying solution to a growing solution and not spoil the fact that the growing solution is still a growing solution. So what, of course, the decaying solution has to remain decaying. So what Sam pointed out is that you have the freedom of redefinition here in the basis functions, in which you can add a decaying solution to a growing solution, and it's still a growing solution. So my decomposition here of tidal field and body response is really not unique. You can redefine it at will, and you have to introduce a scaling constant, lambda here, which has the dimension of length, when you try to do this. But you can apply this redefinition, and as a result of this, what I previously defined to be a love number gets redefined by a way that depends on that scaling constant. So what Sam reminded me here, and reminded us in more general terms, is that, well, if you want to calculate a value for something, you have to define it first, and different people might choose to define it differently, and that's fine. They have different definitions. You will get different numerical values to that thing, but that's fine. It's all equivalent under this class of redefinition that is allowed in this whole business. Now, and to finish the point, well, if you take my choice of basis functions, which I call standard, if you take that choice and you're dealing with a black hole, then you want to prevent this diverging behavior of function B here as you cross the event horizon, and that requires you to kill that term from the perturbation. And that's the origin of the statement that love numbers vanish for black holes. For any other type of material body, that divergence here is of no concern, and you keep that term, and you need that term. But for a black hole, you have to kill it, and that's why love numbers for black holes are 0. But Sam would say, of course, change the definition and change the numerical value for that 0 love number to something else. So nothing sacred about this, and that's just a fact of life. All right. But now let me go back to the point I wanted to make before. So we've promoted this to GR in a fairly straightforward way. What about this? Can we assign more meaning to the love number by defining tidally induced moments for multiple moments to my deformed body? And that's where it gets complicated. So what we would like to do here is to say, okay, we have a love number defined as a property of a deformed metric in this body zone region of spacetime. Can we link that to something that might be observable? For example, something that would enter the binaries equations of motion and eventually would be fed into the waveforms for the gravitational waves that are measured at infinity. So can we link that K2 quantity to a real observable? And presumably that would mean to link that K2 quantity to a useful, meaningful notion of tidally induced multipole moment, or quadrupole moment in this case, for my deformed body. And that's where it gets dodgy and complicated, because we don't have a prescription to do this in GR. In GR, one thing you can do if you have a stationary and asymptotically flat spacetime is to define multiple moments for the entire spacetime, and they're defined essentially at spatial infinity. But what you don't have the ability of doing in GR, at least not a priori, is to take each body separately and define a set of multiple moments for that body. And and when the situation is dynamical and you have a time dependence that comes from the orbital motion, well, we really don't have defined for us in GR notions of multiple moments for individual bodies. So the point is that something that was so straightforward in Newtonian theory is simply not defined in GR unless you find a way of defining what you mean by the left-hand side. I claim that the right-hand side is perfectly well defined in GR. What is not defined in GR a priori is the left-hand side. And that's the source of the difficulty in giving a proper interpretation to K2 and linking it to an observable. Now, people in the past have done, have tried a few things. And one thing that was sort of attempted in the past is what I call a subtraction prescription. And let me explain what it is, and let me explain why I don't think this is a particularly promising way of thinking about this. Well, the prescription prescription is basically this. So we know that one term here in our metric perturbation is growing, and the other one is decaying. If we could get rid of the growing part, our metric perturbation would be decaying, and then we could take a limit where r goes to infinity, and we would have an asymptotically flat spacetime. In that limit, still assuming that we're dealing with a very slow time dependence for the tidal field, we could take a limit, where everything is static, and we could apply the Garrosh-Hansen prescription to calculate multiple moments in this, constructed asymptotically flat spacetime that we get by just killing that growing piece here. So the prescription is subtract out the tidal field from the perturbed metric and compute the Garrosh-Hansen moments from this new spacetime that you've constructed that is now, well, sufficiently stationary and asymptotically flat. Well, I don't like this. I don't like this because, well, it's ambiguous. First of all, the subtraction procedure is ambiguous, and you would have to define what you mean by the tidal field. And it's the same point that Sam made. When you identify the tidal field, you're still subjected to that ambiguity or that freedom of redefinitions. So for you, is the tidal field r squared times a? Or is it r squared times a plus a piece of a decaying solution that doesn't spoil the fact that the solution as a whole is growing and still a very good candidate for the description of a tidal field? So the point is that you still have the same freedom of redefinition up to that scaling quantity lambda here in what you would like to assign, in what you would like to define to be the tidal field. And depending on what you pick for subtraction, you will get an ambiguity in this subtraction that's going to be parameterized by this scaling parameter lambda. So it's a fact of life, and I think it's unavoidable that the subtraction is ambiguous, and therefore it will produce ambiguous notions of multiple moments if you were to apply this procedure. So that's one reason why I don't like this. Another reason why I don't like this is that, well, it's limited to a linearized description of the tidal deformation. You can superpose solutions in the linearized context like this and still get solutions. But if you wanted to generalize this and account for nonlinearities in the description of the tidal field and the tidal deformation, well, superpositions would no longer be solutions to the nonlinear equations. And that means that the prescription is only valid for, in a very limited scope, even if you're willing to live with this ambiguity here. So for both reasons, I find that this is not the way to think about this. And what I would like to introduce here is the way that I choose to think about this, and a way that personally I find is more convincing and more, more robust and more germane to the discussion. All right. My view of quadrupole moments is that they will be defined in a setting where we can describe the mutual gravity between the body and its companion when that mutual gravity is weak. So that's going to be the price of entry here. I'm going to rely on the, on that assumption that I made before, that the interbody separation was large. I'm going to use this as a way of describing the mutual gravity between the bodies as a weak one. And I'm going to use post-Newtonian theory to describe that mutual gravity. So I can still deal with the strong gravity of this body and that body. So both bodies can be very, very dense, very compact, and they can each have very strong gravity. But I'm assuming that the mutual gravity is weak. And that just means that the ratio of m over b is going to be small. And I'm going to use that ratio as a way of constructing a post-Newtonian expansion of the mutual gravity of the two bodies. All right, so what this means in more concrete terms is that what I'm going to do here is to take my body. I have defined the body zone previously. I'm still going to be, playing with that. But now, in addition to the body zone, I'm going to have a post-Newtonian zone, which is the place in space-time where gravity is going to be weak. So we're going to be far enough away from this body and the other one so that gravity will be weak. And that's going to be the description of the weak mutual gravity between the bodies. The post-Newtonian zone is going to extend, beyond my body, beyond the other body, and it's going to be excluding this blue region here that I'm calling the exclusion zone. And that's the region where gravity is too strong to be, adequately described by a post-Newtonian expansion. All right, so that's going to be the setting. So I'm going to argue in the next couple of minutes that this idea of introducing a post-Newtonian zone will allow me to define multiple moments for my reference body. And not only will I have a good definition for them, I will be able to do a calculation to link them to the love numbers. Okay, how do I do that? So when I calculate the post-Newtonian metric in the post-Newtonian zone, I'm doing what people do in post-Newtonian theory, which is basically to solve order by order until you reach an order at which you're satisfied. So you start at 0 pn, no gravity, 1 pn, some gravity, blah, blah, blah. So you just keep going like this. So you do it by iteration, and the Einstein field equations that you use in order to do this is the repackaging that was given to us by Landau-Lifshitz. And on top of this, to make things very, straight, well, not very straightforward, but as technically, straightforward as possible, we're going to be working in harmonic coordinates. And if you do all of this, the main variable that you're going to be solving for here is this Gothic inverse metric that's related to the metric in this way. And the kind of field equations you arrive at, and here I'm insisting it's an exact reformulation of the field equations, Einstein field equations, has the structure of a Laplacian acting on your variables being equal to a source term on the right. The source term can be generated from previous iterations of the procedure. The source terms involve time derivatives of the previously computed metric, and those time derivatives basically bring down or bring up the post-Newtonian order. And we have an effective energy momentum tensor here, or pseudo tensor, that would be constructed from the matter, if you had any, and the field, the gravitational field. Here we don't have any matter because we've excluded all possible matter fields from the post-Newtonian zone because the matter fields live in a region where gravity is strong. So when I work in the post-Newtonian zone over here, I don't have any matter to worry about. And therefore, my right-hand side here is a source term constructed from the gravitational field itself in previous iterations of this procedure. Now the essential idea. When I do all of this and solve the post-Newtonian equations in the post-Newtonian zone, I'm doing this in an incomplete space. My space excludes that blue zone over here. And I have to incorporate information from the blue zone into the calculation somehow. And the way it's done, you can think of this as imposing boundary conditions over here, but it's really the same thing as saying that information about the missing part of your space here has to come through homogeneous solutions to your equation. That is, they have to come in as solutions to Laplace's equation. So information about the blue region here has to be fed through the post-Newtonian zone through solutions to Laplace's equation. And if you think more along those lines, you recognize that, well, what you're going to get are decaying solutions to Laplace's equation. And that's precisely how those decaying solutions, that's precisely how they give rise to a multipole structure for your body here. The multipole structure of the body is something that lives out here in the post-Newtonian zone. The love numbers live over here in the body zone. So two things. So I have a definition of tidally induced multipole moments as quantities that live in the post-Newtonian metric that's defined in the post-Newtonian zone. And I have definitions for love numbers that live in the body zone exclusively. If I can match the two descriptions, match the post-Newtonian metric to my previously shown metric for the tidally deformed body defined in the body zone, then I have a way of linking those two things. The fact that there's an overlap between the post-Newtonian zone and the body zone allows me to do this matching. It's matched asymptotic expansions, and it allows me to relate this description of spacetime here to that description of spacetime over here. And because I have an overlap, I can match the descriptions in that common domain. And that's how I can I can calculate the multiple moments of my body defined over here to love numbers that are defined over here. So that's where we are. So, so my way of thinking about multiple moments is that it's really something that lives in the post-Newtonian zone. They live as quantities that appear in the post-Newtonian metric, whereas the love numbers are some things that appeared in the tidally deformed metric, or the metric of my tidally deformed body. So conceptually, they're defined in different worlds. But because there's an overlap between those worlds, I can actually link the two things. And when I do, this matching, and I carry out the details of all of this, what I find is pretty much the same expression I did, get in Newtonian theory, except that now it involves multiple moments properly defined in post-Newtonian theory, and love numbers that are properly defined in full GR. The matching calculation allows me to link those two quantities. And if I do a detailed calculations, I can account for time dependences, I can account for nonlinearities, I can account for post-Newtonian corrections. And the calculation I did that was in the first paper that I showed you on the title page, what I did is a detailed calculation valid at 1 p.m. order. All right. That multiple moment over here, because it lives in the post-Newtonian world, will appear in the equations of motion that are given in post-Newtonian theory, and it will appear in gravitational waves that you calculate also in that post-Newtonian setting. So that's how you can link a property of the deformed metric to eventually observables, and that link is provided by the match between the two descriptions of the metric. Okay, so now to get to really interesting stuff, can you just say from here that, okay, K2 is 0 for a black hole, therefore Q will be 0 for a black hole? It's very tempting to make that leap, but I can't. It doesn't apply to a black hole simply because when I take my right-hand side and apply it to a black hole, well, suppose that K2 is not 0, suppose I'm applying this to a black hole, then the quantity on the right-hand side, what I have to do is to substitute r, the radius, by 2m. And r to the 5th becomes m to the 5th power. And that means that the right-hand side of my equation becomes a quantity of the 5th post-Newtonian order. The quantity on the left in the calculation that I did was defined at 1 p.m. order. So in order to link the quantity on the left to the quantity on the right, given that the quantity on the right is 5th p.m. order, I would have to refine my calculation on the left and go from 1 to 2 to 3 to 4 to 5 p.m. orders. And I haven't done that. No one knows how to do that at this stage. And therefore that temptation to say that Q is 0 because K2 is 0 is simply not a valid thing to do. So now, in principle, we have this huge barrier. I mean, we have this huge problem that if we really want to say something about black holes in that context where black holes are represented in post-Newtonian theory as, masses with multiple structures, well, it seems that we're prevented from saying anything until we can breach that gap all the way up to, to p.m. order. And for a long while, I thought that this was basically an unsurmountable obstacle until I sort of found a way, I think, to bridge that gap and in fact, go not just to 5 p.m. order, but do it to all p.m. orders. And the way out of that obstacle was to contrive the black hole to be in a perfectly static binary system. The problem with post-Newtonian theory, the reason why it's so hard is because the binary system is moving, and it's very hard to account for the details of the dynamical space-time into the description of the metric. That's where, that's where it gets hard. But if you contrive the black hole to be in a static binary system, you can actually simplify the space-time to such an extent that you can do this calculation, not just to 5p in order, as I said, but to all p-n orders. But of course, real black holes don't want to be in static binary systems. So what do? Well, what I did was to give my black hole some charge. And I put it in the presence of a small mass with some mass and some charge. And what I did was to arrange for gravitational attraction between those two things to be perfectly balanced by electrostatic repulsion. And that's how you can have a perfectly static binary system by just arranging the mass ratio, the charge to mass ratio of the black hole to be the inverse charge to mass ratio of the particle here, so that you have perfect balance between the two interactions. So the exact condition for this is not quite this. There's some relativistic corrections to that, but basically if you have the product of the charges being equal to the product of the masses, then you have this balance of forces and you're in business. Now you might say, well, this is crazy. I mean, black holes don't have charge. Why would you want to do something like this? And I'm going to argue in just a minute that, well, maybe it's not so bad, because if I take my particle here to have a very large charge to mass ratio, then the charge to mass ratio of the black hole will be correspondingly small. And I will be arguing that, if I put a small amount of charge in that black hole, it's not going to change its properties by very much. And in particular, it's not going to change its tidal response by very much. So I can really make use of this, sort of crazy idealization, this crazy contrivance in order to make progress. Because when I introduce this situation over here, I can consider that space-time to be a perturbation of Reissner and Nordstrom. I can take this to be a small mass and a small charge, albeit with a charge, large ratio between the two. And I can introduce this as a perturbation of Reissner and Nordstrom and calculate in all great details the perturbation, combined electromagnetic and gravitational perturbation of that Reissner-Nordstrom solution. And that describes, in part, a tidal deformation of that black hole with a tidal perturbation, with the tidal field produced by this companion. So that's what I do. And what do I get? Well, there are lots of steps involved. So I do the full, GR calculation as a perturbation of Reissner-Nordstrom. Then for technical reasons that I've explained, I have to convert to harmonic coordinates. Then I can take my space-time and expand in post-Newtonian orders. And once I have that, I can read off the multiple moments as I've defined them previously. And when I do all of this, the final result that I get is that all tidally induced multiple moments for that black hole vanish to all p-n orders. And now, finally, through that, I can make a link between the multiple moments and the love numbers and see that they both vanish in their respective worlds and therefore establish a connection between the two worlds. Now, admittedly, this is contrived. I mean, my static binary system is never going to be realized in nature. So can I convince you that that result will continue to apply to real astrophysical black holes in real binary systems with motion? And I can't prove it, but I have arguments that convince me at least that the answer to that is yes. One aspect of this is that the relationship between Q and curly E should be generic. A natural tidal environment and a contrived tidal environment will translate into different expressions for curly E. But the relationship between Q and E will be generic. It will apply to any tidal environment. And if you get 0 for one, you'll get 0 for the other. So that's the first part of the argument. Maybe you're not happy with the fact that my binary was static, and you will question the the limitation associated with that. But to that, I will say that the static limit really captures a leading term in an expansion of this tidal deformation in that ratio of timescales. And that was true in the Poisson calculation, continues to be true here. So if I can do a static calculation, I don't have everything, but I have the leading term in that expansion. And finally, as I said before, well, maybe you don't like the fact that I had to put charge into my black hole, but then I argued that, well, the charge to mass ratio can be very small as you wish it to be. Of course, it cannot be identically zero. All you have to do is to introduce a particle that has the exact opposite charge to mass ratio, and you're done. And my clock here tells me I'm out of time, so I will just flash my conclusions and leave it at that. So thank you very much for your attention.
Thank you for the really nice talk. So I think there is time at least for a quick question, if there is one. So I don't think that there are questions at this moment. So I have a quick question about the relation between, so in your slide before the conclusions, can you elaborate on why the relation between the Q, so when you say, the next slide, when you say that the relation between these two quantities is generic, can you elaborate a little bit more about why? I didn't.
Yeah. So if I go back to neutron stars or things for which I can calculate, in the confines of post-Newtonian theory, what I'm saying is that, well, here it doesn't matter what I assume to be the state of the binary system. It didn't matter whether I was dealing with circular orbits, eccentric orbits. Didn't matter what kind of mass ratio I was looking into. That relationship that you get between the tidally induced multipole moment and the tidal field is always the same. And it always involves those ingredients, regardless of what you provide as information about the state of the tidal field. That's what I meant by being generic. So that relationship will always be the same regardless.
Okay.
And I'm arguing that the same should apply to the black hole case. And if it's zero, if Q is zero for one E, however contrived, then I would tend to believe that it's going to be zero for all tidal fields that would be less contrived.
Mm-hmm. Okay, I understand. So now it's not it's reasonable to assume that this is going to be true for black holes, right? So that's I didn't understand. I didn't understand at the beginning if it was a result that this was generic or it was something like very plausible, as you said. So
it's an argument. So I wish I had a proof, but it's an argument. Yeah.
No, okay. So I think so. There are two hands raised. Okay, so Shinji, if you want to unmute yourself. Next,
yes. Eric, thank you for the very nice talk. And
hi, Shinji.
Hi. I want to ask a very probably stupid question. So you mentioned that your relation is universal, and in order to test this universality, can you try to consider a pair of extremal black holes?
Yes, and in fact, that would be that would be easy to do because we have the Majumbar-Petru solution for this. Mm-hmm. I didn't look into this specifically because I really wanted my charge to be as small as I could, and I really wanted to argue that in the limit of very small charge we would get something mm-hmm. sensible. But you're right. I mean, it would be very straightforward to verify, or to check that that expectation in the opposite regime, which would be the extreme regime.
Yes. Yeah. Thank you.
Yep.
Okay, so we'll have more time for questions in the discussion session. So thank you very much for the talk.
Thank you.
We're going to move forward to the next speaker. Yeah, so next speaker.